turn on the microphone. So thank you very much for this kind introduction and the invitation to give this seminar. So let me share the screen and then full screen now. Okay. So I see a lot of people are coming in or still. That's good. So we have a large audience. I think, as you said, questions after the talk, but I guess you can also write something in the chat and then later so we don't forget it. Yeah. Okay, so the title or the topic of my talk today will be how to possibly constrain the high density equation of state of QCD from heavy ion collisions and heavy ion observables. And this is a project which basically goes back to also my first works as a doctoral student. So I've been interested in this for a very long time, and I think the whole community has been interested in this. And so of course, I didn't all do this by myself, but there were many collaborators and students and professors involved. So of course, this is not all my doing, but a lot of people contributed to this. So just to give, I mean, you've seen these sketches many times, so but I think it's still important to show another version of it. And that's basically because that's what I think the community is still interested in. So to find out what are the states of hot and dense QCD matter and how can we probe them. And if you look at this, so this is a sketch I made, we kind of know already some things about very low density and high temperature from lattice QCD, right? So we know that there's a crossover here around 150 to 160 MeV. However, these methods, they kind of break down as we go to higher density, and all we know at higher density is that we have a nuclear liquid gas transition at very low temperature. And who knows what at high density and high temperature. That's not very well explored, and I think that's kind of the focus of a lot of experimental programs in the near future. And the good thing about this, and which makes it a little bit unlike other fields, is that there's a lot of room for speculation still. Right? So you cannot, since you cannot exactly calculate things, that sometimes is a bad thing because you cannot calculate it. But it's also a good thing because you can imagine new things and maybe think of interesting or exciting new things to discover. So before I come to the phase transition and how to really describe heavy ion collisions, let me first give a very brief, recapitulation of what we know about QCD thermodynamics at low baryon density and why we really cannot extend this knowledge much further than we already have. And that knowledge basically comes from the last, let's say, 10 to 15 years, comes mainly from lattice QCD. And lattice QCD, of course, you try to solve QCD on a space-time lattice, and it's very computationally expensive, and you have to take very great care about all the numerical artifacts you have. But I mean, that's why it's good you have different groups working on this with different approaches. And what we have found, or what was found in the last year, so this is from 2014, or it's basically when things started to converge, is that we have lattice results which are reliable for temperatures above 130 MeV roughly. And what they calculate here is the interaction measure, which is the energy density minus 3 times the pressure over T to the 4th, which then can be used to calculate the pressure and the energy density and the entropy density and so on. So all the thermodynamics that you want. And what you also can calculate on the lattice is basically now derivatives of the pressure, or derivatives of the pressure with respect to chemical potential. In particular, also what you can do is an expansion into finite real mu b using these derivatives, but you can also do calculations at imaginary chemical potential, which can be helpful for some cases. So this is what we know. We know kind of what you see here. There's a strong increase in this interaction measure, but it's not a jump. So we know it's kind of a crossover transition. And now we want to know how this changes as we go to finite density. So one interesting, and I want to just mention one word which I think was very interesting, very helpful in understanding this, is doing different expansions of the thermodynamics into the finite density, but also finite imaginary chemical potential. And so there's two different ways of expanding. Either you do a cluster expansion. So a cluster expansion is also sometimes known as Meyer's cluster expansion, is when you basically take your density, you scale it by the temperature, and then you just write it as a Fourier series. Right? So you have these Fourier coefficients, and then you just have some sinus hyperbolicus of mu b over t. And so this is basically this cluster expansion. And what you can do, you can calculate these, or you can measure these coefficients from the lattice with very high precision, so that these are these points which were published already some years ago. And the interesting part is if you go basically low temperatures or up to 180 MeV, these points are very well described by a hadron resonance gas model. And above they diverge, which you would expect. And then of course you do these arrows, they are basically what you think are the limits, asymptotic limits. So assuming such a proper limit, Stefan Boltzmann limit, one can basically approximate these coefficients very easily by this little formula, which only depends on the first two. So let's say if you have the first B1 and B2, you can actually write any coefficient using this formula, and it works very well to everything which has been measured by the lattice. And you kind of also assume that you have to get to this Boltzmann limit. So that means, so now I can, by this assumption, you can calculate all these coefficients, but what you can also do, you can use these coefficients to calculate now a different set of coefficients, namely these susceptibilities, which can be used then to do an expansion, a Taylor expansion in finite chemical potential. And that's what was done in this paper here. And what you see here is, again, these are 6 different orders of Taylor expansion coefficients. So 2nd order, 4th order, 6th, 8th, 10th, 12th. And so basically, the only one where lattice data exists until now, I think, is up to 6th order, which are these green points. And the red points is basically what we get from this approach and using the BK measured from lattice and just connect for the first 2 terms and then connect them then to higher orders using this formula. And you see that they actually work very well up to very high order. Right? So, and the thing is, what you can do now, you can basically now calculate your susceptibilities to arbitrary order. And so why is this interesting? Well, it kind of gives you an idea of the radius of convergence of your whole series. So why is this interesting? Because you want to know how far can you drive at maximum, even if you go to, if you were able to measure from the lattice the 100th order of your expansion coefficients, how far can you actually go? And what you get is that the radius of convergence of, if you do an expansion in mu b over t, is always less than pi. And that's because there is a well-known with the sound. Okay, there's a well-known singularity in the imaginary plane of this phase diagram, which kind of limits the expansion. So even though it is an imaginary part of the phase diagram, which is not accessible by physical methods in experiment or anywhere, because it's an imaginary part of the chemical potential. However, you still cannot drive your expansion beyond this radius, and that's a problem. So this kind of gives you a natural boundary for this expansion. And so this is basically what you do, right? So what they did, so they wrote the expansion of the pressure using these susceptibilities, which I was just talking about, and then you just expand the pressure in the different chemical potentials. And again, if you don't use this method with the cluster expansion, but just try to measure this brute force on the lattice independently, what you also find is that if you do this expansion and these artifacts or numerical artifacts appear around, again, a similar mu b over t, 2.5. Now I think they say they can go up to 3 or something, again, somewhere around pi. And again, the radius of convergence never goes beyond this magical number. So again, it seems like whatever you do on the lattice here, you will not be able to expand beyond this magical boundary of mu b over t more than pi. You still can use these for interesting results. I'm not saying that this is not interesting. I'm just because you could, for example, still study things like quark repulsive interaction using these susceptibilities at low chemical potential. However, that means that if we want to really know what happens at high density, we have to use different methods. So what's the strategy? So the strategy then can only be we have to rely on some experimental observations, unless somebody comes and has a genius idea how to solve that is at finite chemical potential and solve the sign problem. That's of course always the option. But unless that happens, we have to rely on experimental observations. And even if we do the calculations, we still have to confirm them experimentally. So what we want to understand is actually QCD matter, not neutron star matter or heavy ion collision matter. Those are basically the same thing, just a little bit of slightly different isospin and used as input for simulation. But what we really want to understand is the properties of QCD matter, which is the underlying theory. So the one approach you can go by, and at the very end, I might give you the opposite way, but the usual way of how people are doing this is some kind of top-down approach where you start with calculating or constructing an equation of state that can be used for finite temperature density QCD matter, and then you do consistency checks, with known properties at small mu b over t and nuclear matter properties. So that's already a big challenge, but this you can do, right? So you can construct your equation of state in the way you want. Then you implement this equation of state in a consistent dynamical model for heavy ion collisions. Okay, and then you use this one equation of state to calculate different heavy ion observables. And here the emphasis actually should be on a complete picture, because it doesn't help you if you just calculate one observable and then this works for one equation of state, and then for another observable you get a different equation of state, and then in the end you don't know what you get. So here it's really important that because we have this big wealth of experimental data in heavy ion collisions nowadays, it's really important to use that, right? And see and try to find a consistent picture of everything. And then if you want, you can still go back and cross-check with the astrophysical observations and see whether this also checks out. And only if you have all these puzzle pieces in place, then you can claim, okay, I found something, or I've made a discovery that I think this is how the equation of state looks like. And of course, you can also do this to reject unlikely equations of state, because in the end, it's always hard to find the truth, but it's much easier to find things that are wrong, right? So if you rule out a lot of things, that might be much easier to do. So what I will give you an example of how to start off with. So I will go basically through all these points now and how we try to do it. Of course, other people are invited to do it their way. Absolutely, this is how the scientific community should work, right? Not only one group does everything, and then it's the truth. No. You have to have different groups with slightly different approaches doing similar things, and hopefully in the end they converge on one picture. So what we did is we said, okay, first we have to decide on some model to give us the equation of state, and for this we used what we call the effective SU3 flavor chiral mean field model, or short CMF. And I don't know, maybe in our collaboration you can invite Anton Motomenko at some time. He will give you a more detailed introduction on this model. I will just try to go through the basic ingredients. And so the idea of choosing this model with this long name was that it's a model where you can kind of plug in a lot of things. So I remember one person once called it's like this walking castle from this anime. I don't know, because it has so many tubes and buttons and dials you can deal with. It's almost not understandable, but on the other hand, that's the advantage. You can really change the properties of the model as you think they are true. So what it is a chiral model for hadrons, and chiral symmetry here is restored via parity partners. That means you have your ground state nucleons and you have your parity partners, and the signal for chiral symmetry restoration in that sense would be the equality of the mass, and that's what you see here, and that's what observed on the lattice also. So this is the nucleon mass as function of the temperature from the lattice. So you see it kind of stays around the vacuum mass, so it's divided by the vacuum mass, so it's a 938 MeV. And then you have this parity partner, which is the n star 15 something. And you can see here, so that's the mass of the n star, which drops down towards the mass of the ground state nucleon as you approach the pseudo-critical temperature of chiral symmetry. And that's kind of the idea nowadays on how we think chiral symmetry is restored in the hadronic phase. So that's something we put in. So that means we have some effective masses for the baryons. And so there's these different coupling parameters which you have to adjust. And you have to have a scalar potential which kind of governs the dynamics of these scalar fields which are responsible for the mass gap of these two, and so on. What you also can fix these parameters to plus the repulsive interactions to get your nuclear ground state matter right. So you can have the binding energy as function of density, right? That's something which is known, so you want to do that. And then, of course, you have to include, because at some point you're not just in a hadronic world, so you want to include some quark matter, so you have to include deconfined quarks and gluons. And there was a model which was called this Polyakov loop or PNGL model, which we took at least to some parts and included basically the contribution of the quarks, which is suppressed at low temperature due to this Polyakov loop potential down here. And interestingly, in order to remove the hadrons at high density, we included an excluded volume mechanism, so we can smoothly transform from an equation of state from hadrons to quarks without needing two different models. And what you get in the end then is you fix again also the parameters of this to describe your lattice results at zero chemical potential, like here. So the red line is our model, and the green bands are the latest lattice results. And then if you go back to, for example, also want to describe neutron star matter, it's the same model. You can do it. You just set your temperature to zero, set your isospin to, or basically turn on beta equilibrium. And then you can look at the different abundances of, let's say, quarks up here and neutrons and protons here as function of the chemical potential at zero temperature. And then you can see how, as the quarks appear, slowly the hadrons disappear, and we get this very nice smooth transition from hadrons to quarks. So that's what we put in. So this was also applied to cold matter. So as I said, the compressibility or incompressibility of this equation of state is fitted to some values known from experiment. Symmetry energy is matched to what we know. And what you see here is the speed of sound, for example, for neutron star matter or for heavy ion collision matter here from this model. So you can see how it shows this maximum and then goes back down at higher density. So this is something very interesting, because you basically have first the hadrons, which make the equation of state stiff, and then the quarks start coming in, which soften it again. And what we also find is our mass radius diagram. You're putting this equation of state into the Tolman-Oppenheimer-Volkoff equation. You can calculate the mass radius relation of neutron stars, and what we get that this is also consistent with known constraints. So we now have an equation of state which more or less is consistent with a lot of known phenomenology of the phase diagram. Of course, it's completely constructed. It's by construction. It has parameters, and therefore that's all we can say. However, one thing you can use this for, which I found very interesting, you can use this model to maybe understand why these methods, these lattice methods, actually break down. And that's what we did here, is we calculated lines of constant pressure in the temperature density phase diagram. And you can see, as you are at low density, these lines are almost horizontally, right? So they don't have any dependence on density at low density. That means that your matter is really dominated by those degrees of freedom we don't care about density, which is mesons or gluons, or QQ bar pairs. And if you then go to higher density, then these lines immediately shift and become vertically, which means that temperature doesn't really matter. And so what that means is, if you now plot the line of mu b over t equals to pi, where basically we know our expansion breaks down, you more or less follow this line where this whole dynamics changes. So basically what we are saying is that all these methods break down at the point when we are going from the boson-dominated matter to fermionic-dominated matter. That's where the calculations seem to fail, where the multi or baryonic interactions become important. Right? So on the positive side, this is good, because what this means that for the region of interest, which is this region here, which we don't know anything about, just the density-dependent equation of state might already be a good approximation if you want to learn something in the models. And now we will go on and see how we can put this in. So how do we access now the phase diagram? Okay. So I draw on the right-hand side a phase diagram from what we know and how we can study it. So that temperature, density, and down here, this little nose, this is the nuclear liquid gas transition or coexistence, right? So that's what we kind of know. And so what we can do is we can use, as I said, we can use the mass-radius relation from neutron stars, and what we get then here is we learn a little bit about the equation of state at zero temperature and up to maybe 9 times saturation density. That depends really on the equation of state a little bit, but roughly that's what you get. Okay. And there has been these recent papers where people actually started to constrain the speed of sound, as you can see here. So that's something very nicely. They use now really statistical methods to do this, and this is quite helpful. But again, this is from pre-merger, so this is not from neutron stars, but it's also from neutron stars, but it's not from stable cold neutron stars, but from binary neutron stars and how they interact with one another before they start merging. And just want to mention Shriya Soma and Kai Zhou. They recently published a new method on how to use machine learning methods to do this also in a similar way. What you can also do is you can use binary neutron star mergers to turn on the heat. And there we kind of did something also recently. And what we found is that in these kind of mergers where you have the 2 neutron stars which rotate and then they start touching and they heat up when they basically touch in this interface, there you get entropy production. But what you get is that you maybe reach, using the CMF equation of state in the simulations, what we get is that you get temperatures which are up to maybe 40 MeV. And that's basically indicated by this blue region here, or here on the left-hand side. This is basically a time-integrated evolution in the temperature and density plane for these mergers. And you see you get entropies of about 2, or entropy per baryon of about 2. And then we try to relate this to what would be the corresponding heavy ion systems. And then you get, okay, maybe if you have beam energies of 450 to 600 MeV per nucleon, that's basically what a system which is comparable to a neutron star mergers. But you already see here at the finite temperature, we don't go to densities maybe above 3. Right? So if we have a phase transition which is higher, then with this merger, we would miss it at least at the finite temperature. And we don't really know yet what exactly are the observables in the neutron star mergers for the equation of state. That's also another topic, a completely different topic, but also interesting. What you can do is you can also look at core collapse supernovae, which means you have a very big star which collapses into a black hole. And by doing that, it kind of creates a lot of stuff which is emitted outwards. And you can do also the general relativistic simulations, again, using the CMF model. And again, here we see the density versus temperature. And these are different trajectories. And what we found here is that, in fact, in these core collapses, you actually can produce much, much higher density and a little bit higher temperatures, which is nice. So this is kind of, in addition to the neutron star mergers, now we have this region here covered, but still, I mean, temperatures are not super high. There we also then now have to think about what are the observables here. Nobody has really studied this, or some people have studied this, but I think there's still a significant amount of work which can be done finding out what would be the observables in these kinds of events. Now, finally, coming to the heavy ion collisions and how we want to do it there. So now the question is, when we have our effective model, we believe it or don't believe it, that's up to everybody to decide. Question is now how to study the equation of state using heavy ion collisions. And much of what we think about today about heavy ion dynamics is motivated by this fluid dynamic picture of heavy ion collisions. You probably heard this many times. So what's the fluid dynamic picture or the standard model of heavy ion collisions? Well, you have to basically say you have some non-equilibrium or pre-equilibrium initial state, which is calculated either by some transport model or some Glauber model or some simplified model for the gluon dynamics in the initial state. And once after a short time, the energy density and momentum density and asymmetries and all the distributions that you generate from this initial state are put into some hydrodynamic or viscous fluid dynamic model. And then this evolves until a point when you say, no, if say, okay, at this point, stuff is not in equilibrium anymore, in local equilibrium, and therefore we have to do something else. So you go to the final and freeze out stage, which is, again, usually done by some transport model, and then stuff can be measured in the detector. And this type of model has been very successful in describing heavy ion observables at ultra-relativistic energies, I would say above square root S of 10 GeV, roughly. The problem is that the equation of state that you probe in these collisions is what you basically already know from lattice QCD. And if you want to go to the high density baryon-dominated region, you have to go to lower energies. And what happens at lower energies or the most important thing is what you see on the left-hand side here. So we already knew this some years ago, but we really never cared about it. But what you see is that the starting time of your hydro evolution, if you go to beam energies below, let's say 20 GeV, is that the starting time suddenly becomes very large. So what does that mean? That means that your nuclei, when they collide, they take a very long time to actually compress and go through each other. So, and that time can become much longer than the actual hydro evolution itself. So a lot of the dynamics, which is sensitive to the equation of state, happens at this early time, which you don't really know how to describe it, or you know maybe about how to describe it, at least not in these standard models that are being used. Right. So what we did is we said, okay, let's maybe get a different standard model. So what we try to do is try URQMD, which is a fully non-equilibrium transport model. And this has a cascade mode, which most people use, for example, for the final state hadronic phase, where you just do scattering and follow a straight line until they scatter. And the equation of state resembles basically hadron resonance gas. So as I said, what you have 2-to-2 collisions, 2-to-1 collisions, 2-to-n, and 1-to-n basically decays, interactions which are allowed. You can fix all these parameters from particle data book group values, and you do a lot of guessing. If, to be honest, you have detailed balance mostly, but violated in string excitations, annihilations, and multi-particle decays. So that's the model which most people know. And in this model, the particle production mostly goes through the excitation and de-excitation of resonances, but okay, you might know this already. But what is also interesting is that this has a large number of resonances. So this is just a list of non-strange baryonic resonances which is included. So you have a lot of particles with a lot of parameters, and again, you have to find some way to fix them if they're not available. And again, I will skip this. The question now is, now we have this model, but it only resembles the hadron resonance gas, right? So you want to put in some interesting equation of state into this model, and hopefully then you can describe the whole dynamics, including the compression phase, with some interesting equation of state. And so we asked, how can we implement any density-dependent equations of state into EoQMD. So in principle, you would also have to think about a temperature and density-dependent equation of state, but that's already complicated. So we said, let's start with the easy part. So let's try density-dependent equation of state first, because again, as I said before, maybe for the interesting physics at high density, a density dependence is the dominant part, and it's enough if we do this, start with this. So what you do is to get this real part of this interaction density implemented by a density-dependent potential V, which is shown here, for example, 3 different parts on the right-hand side. You just have to have this V, sorry. The phone was ringing. And you kind of want this potential to describe your nuclear matter down here properly. And the solid line is then basically what we get from the CMF model. So we basically take the CMF model, we calculate our field energy per baryon, and then we subtract our free Fermi gas. And what we have left over is what we call the VCMF, right? So that's kind of our way of implementing the CMF equation of state into EoQMD. And once you have this potential, you can calculate its derivatives, you can calculate the pressure, you can solve your equations of motion. So these are basically non-relativistic classical Hamiltonian equations of motion. And a phase transition can then also be very easily implemented by just adding another minimum into potential energy, like in these dashed lines. And what this then does is, as you can see here in the pressure, it leads to these regions of negative pressure gradients, which are unstable regions. So this will lead then to phase separation and clumping, all the nice things you would expect for a phase transition. So once you have this, what we did is we included this CMF equation of state in EoQMD and compared it to a hadronite resonance gas baseline. And on the right-hand side, what you see here is the evolution of the net baryon density for 5 different beam energies. This is the lowest beam energies, which is available right now at the hardest, the GSI. Then it's 2, 4, 6, 10 GeV in the lab frame. Again, and what we did is, so the solid lines are our EoQMD simulations in the upper part only with the cascade mode and the lower part with the CMF model. And you already can see there's a big difference here when it just comes to the maximum compression, which is reached at the different beam energies. But we also compare our results with a full hydrodynamic simulation where you just run the initial state up to the end in the hydro, but you can also put in the same equation of state. And you can see is it specifically for the CMF equation of state, where we put both equations of state in explicitly, it's almost identical. And it tells us how nicely this approach actually works. And what you can do with this, we can actually already plot what is the maximum initial compression now in the phase diagram using this CMF equation of state. And that means we're kind of able to study all the phase diagram to the left of this purple curve. So that was already a nice finding. Now, coming to possible observables now is really the next interesting part, right? So we want to calculate things. So and there's many observables which has been discussed, and I will go through a few of them. So as we've seen before, the bulk evolution works properly, and now we can first look at flow, which is much more sensitive to the details of the equation of state, right? And again, it is the advantage is that now in our EoQMD, we don't have to deal with the uncertainties like the particleization, initial state, or transport coefficients. So one example is the V1 story. So you might have heard this, and you know that early studies proposed that the directed flow, which is basically this bounce of in the in-plane direction of your collision, should serve as a signal of a phase transition. And these were done using 1 or 2 fluid dynamics. And this is now here, this is how V1 is determined. It's just the average Px over Pt as a function of the rapidity. And when you then calculate the derivative of this V1 with respect to the rapidity and plotted versus as function of the beam energy, then it was said that, oh, if you have a phase transition, you should see this kind of minimum. Now, recent star measurements have shown that there might be some kind of negative slope. So this is for the protons, the slope of the V1, and you can see it goes negative. It has a minimum at some energy, although the actual value is very slow. And this is the standard EoQMD simulation. So the question is, does this signal a phase transition? So what we did is we use our CMF equation of state and two different phase transition equations of state and calculated it. We calculated not only V1, which is on the right-hand side. So here the solid line is actually always the standard CMF equation of state, which has a crossover, doesn't have a real phase transition. And you can, these two are the ones with the phase transition. And we also find if we put the phase transition in transport model, no hydro, full transport model, non-equilibrium, you also get this minimum, which was expected, but it's much, much stronger than as you would expect in the data. On the other hand, we also see results, strong effects on the elliptic flow here, right? So the if you put in a phase transition, elliptic flow increases significantly, but also on the mean transverse velocity or mean transverse kinetic energy. Like this, it is reduced significantly when you have a phase transition, which is also something which you would expect. However, what we found in these studies that we only are sensitive up to about 4 times saturation density in these regarding the equation of state. But it's still, I think it was a very interesting result. Then we went on, we said, okay, flow is not everything. We have a lot of observables. For example, the called Ainbury-Brown twist femtoscopy. And that's basically a 2 charged pion correlation. So you're kind of correlating same charged pions. And then with this, you can basically study the emission dynamics of your fireball. And you would expect that if you have a phase transition, then maybe the fireball would live longer. And if you have a very stiff equation of state, then it would expand faster. And this would then have observable effects on these correlation functions. And that's what we did. So we calculated, again, did our simulations. We calculated the pi plus HPT radii, which are called R out and R side. These are just perpendicular vectors in this correlation function. And what we see is basically just look at these lines down here. These are the lines where we do not reach the phase transition. We have the cascade model up here, which has a very different behavior. And cascade model you can basically consider as a very soft equation of state. And if you have a phase transition, you basically go from here, which is stiff at low energies, to something which is very soft. And then it becomes stiffer again. So we saw this very clear dynamics here. And if you now look at the data, so the data down here has very large error bars, which is a problem. So you cannot say, does this actually fit the data or this? However, there's these 2 little triangles here and here, which are the newest star data points with very small error bars, and they seem to indicate a rather stiff equation of state. So again, you only see sensitivity up to 4 times ρ0, 4 times saturation density, but still at least there are differences, and it's consistent with the flow. Third one I want to show, we still have a few minutes, that's good, is electromagnetic probes. So what I'm talking is dileptons, and the idea here is very sophisticated, as you can see from this bowl of soup. So basically what you say, you treat your heavy ion collision like a bowl of soup, and then you say, well, this bowl of soup has a given temperature and density, and at this given temperature and density, I can emit electron-positron pairs from the thermal heat bath. And since these guys, they interact only electromagnetically, they don't really feel the medium around them, so they can immediately escape. And by this, you say, I can study the properties of the system at a very early time, because hadrons only probe the final state properties of the system. So what was done here is, again, this is an older simulation where we were still using hydrodynamics, but there we already saw that in left-hand side without a phase transition or right-hand side with a phase transition, the system would emit at different times, at different temperatures, at different densities. And what was found there is, just look at the right-hand side plot, is that we got about a factor of 2 enhancement of the dilepton or E plus E minus rate at certain mass range if we included the phase transition, which just would sit there and boil and cook and just emit dileptons all the time. Now what we did here is we try to repeat this kind of study, but now again consistently within the QMD model with the phase transition, which already, or with the CMF model, which already we've seen works well for flow, works well for HPT radii. And what we see here is also, again, if we look at the phase transition 1 or phase transition 2 scenarios, we get a strong enhancement of the total measured dilepton yield normalized by the pion number. right? So this is going from 1.7 to 2.3 or so, right? I mean, it's not a factor of 10, but it's at least something. And if the experiments are sensitive enough, they might be able to measure it. That's really nice because, again, you want to find many observables and make them consistent with each other. Finally, I'll skip that. Finally, I want to say now, of course, what I did now, I just said, oh, this is the equation of state I believe in, or 2 or 3 of them, and I test them, and then I compare them with data, and then I by hand can decide what is the right one. This is how people have been doing it for a long time. But of course, there's other ways of doing it, and more modern ways. And one way of doing it is using Bayesian inference methods. And this was done in collaboration with student Manjumnath and Kai. And what we did here is, instead of just saying, I believe this equation of state, I believe that equation of state, we just say, let's just parameterize our equation of state in terms of this potential. So we can find an infinite amount of polynomials which kind of extend this equation of state, which is known at the low density region, but we just take a lot of them. Then we plug them into our simulations we run, and then we have a very large number of different observables. In this case, we were just using the MT and V2 as input. And then we let our Bayesian inference try to find what is the most likely equation of state here, assuming that the data are correct and assuming that the model is the proper way to connect this input to the data. And what we find is, if we actually take all the MT and V2 points which are available, we get this red curve for the speed of sound. And as I show you here, this gray band is the constraints from neutron stars. So this seems actually quite interesting because it looks very similar, that we have this maximum here at several times saturation density, and then it goes down again. However, if you just remove 2 points from this, 2 MT points from a measurement which is a little bit older, suddenly the model gives us a very different curve, which would also indicate a phase transition. And that's a problem, because that means that there's a strong tension in the data, and just from taking all data as equal and putting it in, it's very difficult to say what is the true equation of state. And this, I think, is a problem which will be solved in the future with better and improved data coming up. But at the moment, I would say this is still a problem that depending on what data you choose, you might get very different answers. Okay, so I think that's good. So to summarize again, so what I try to really convince you is that we still haven't given up in using heavy ion collisions and binary neutron star mergers to scan the high density QCD phase diagram. And I think especially for the heavy ion collisions in the FAIR or HIAF or beam energy scan 2 regime, we need new ideas and methods for old and new models, right? So these models have been around for a long time, but we need to kind of bring them up to date to a point where we can now implement these different equations of state and make predictions for models. What I showed you in this work is, first of all, that the phase transition and transport model actually shows an effect on the observables. The best results obtained are for model without a phase transition, but with a crossover consistent with astrophysical observables, which is nice. And what we also need to keep in mind that only these consistent models can be used for future statistical analysis of the large data sets, right? So we have to make sure that the model kind of is self-consistent. Again, there's still room for a lot of development of critical phenomena, relativistic treatment of transport models, and so on. But let me just point out one thing before I'm finished. Yes, one surprise at the end. What we also found is that, for example, the minimum of DV1 coincides with the maximum of the dilepton emission, the HBT effect, and the maximum of the fluctuation enhancement seems to occur at even lower beam energy. So that means that these effects don't occur at the same beam energy, again, which highlights the need for this consistent description over many or different energies with different systems and so on. And now that's it. I thank you very much for bearing with me, and I'm open. I think we're open for questions, right? Thank you.
Okay, so yeah, thank you very much for your very nice talk. And any questions? Yes, you can raise your hand in the Zoom or any question here.
Yes.
Please. Yeah, I can go first. Hi, yeah, I'm Kaijiao. Yeah. So I would.
Hi.
Yeah. So could you give any conclusion about whether this transition occurs from your study on V1 and HPT to be the data show signal for the phase transition?
Yeah, so I didn't show this actually. So when we did this Bayesian analysis, in fact, what happens this red curve, which has no phase transition, also works best if we then compare it to the V1. So it seems like the V1 also, even this, the funny thing is you can get this little minimum, which is there for the star data. You can also get it without having a first order phase transition. You don't need it. Only if you want to have a very strong dip, then you kind of need to have the phase transition. And for the HPT, it's really, the problem is that the only points for the HPT which are really have small enough error bars to say anything is this point here at, was it 4.5 GeV and then 7.7, and the other ones, I mean, the error bars are basically consistent with anything. So here we need to, I think we need much better data on this for the HPT in the low energy region to say anything. There's the hardest point down here, which is below everything. This is absolutely not understood, I think. But also, there might be some issues with this point. But again, HPT looks like it's favoring a rather stiff equation of state at high densities, high energies. What happens here in this low energy region, I don't know, right? I mean, it could be anything.
All right. So I have also a technical question about how you treat hadronization, because when we're talking about transition from QGP to hadronic matter, there's a hadronization which converts the quark gluon degree of freedom to hadronic degree of freedom.
Right.
And in particularly, if you have a phase transition, first order or second order phase transition, how do you convert quarks and gluons into hadrons?
Yeah, so that's a good question. So for our current work, we do not, we have a phase transition in a thermodynamic sense, right? So that means that we have two coexisting phases at different densities. However, we do not change the degrees of freedom. Right? We don't have the aspect of deconfinement in yet. So in both cases, these two different densities, we have basically the basic degrees of freedom of URQMD, which are the hadrons, the nucleons inside. But so it's basically some kind of hadronic phase transition, right? So we don't change the degrees of freedom. And to your second question, most of the cases I showed you here, these are phase transitions which basically don't have a critical endpoint because they're very strong. We wanted to make a very strong effect and see and compare this. In principle, there in our paper with the flow, there we also included equations of state with Agnieszka Sørensen and Volker Koch, who have a equation of state that has a critical point around 100 MeV or so. So in principle, that is included. However, when you talk about, again, critical phenomena near the critical point, then correlation length and the range of the interaction becomes very important. And that is something, it's not so clear how to model this in this transport model where the interaction range is determined by the width of these Gaussian wave packages, which are not changed in this during the whole simulation. They are fixed by comparing to nuclear matter properties. But maybe near the critical point, one has to change them and to see these critical phenomena. So I'm not sure about critical point stuff here, but I can tell you the phase transition stuff is okay.
So you are simulating the quark gluon plasma phase by using adjusting the interaction between nucleons, right?
Right.
the high density phase, right?
Yeah, so basically we're simulating a QGP by changing the interactions of the hadrons. So you can do it up to a certain point. At some point it becomes not doable anymore, but up to a certain point you can do this very well. I mean, you know also from hadron resonance gas, if you put in interactions there, you can kind of go into the chirally restored phase to a certain point and mimic the interactions of the QGP with the interacting hadron gas.
Yeah, but you CMF model, which includes the PNGL model, right? Which is for parts and groups. Right.
Yeah, right. But that's why we say, okay, we change this potential by using the CMF potential and subtracting only the free hadron gas. And so we basically say all the change of degrees of freedom and the interactions kind of just enters into this effective potential. So even though we don't even change the degrees of freedom themselves in the QMD. So it's
okay. Thank you. Yeah, thank you very much.
Thank you. So there's more.
Okay, so next, please, Yan, please. Hi, yeah. For the talk. I have a question also on.
There's some feedback right now. I cannot.
Hello? Hello? Can you hear me?
Yes, a little bit, yeah.
It's better now?
Yeah, it's much better now. Yeah.
Okay, good. Yeah, thank you for the talk. Yes, I have a question also related to this slide. So first of all, if you construct the equation of state from the effective potential, here this the phase transition you refer to are all first order phase transition, if I understand correctly?
Yes.
Okay, that's right.
Actually, yeah. I mean, actually, this this solid curve actually has a crossover.
Yes, I thought I had crossover. Yes. Okay.
Yeah.
So maybe I got lost here. Is how do I see the effect of temperature in this potential here?
Yeah. So in this potential, you don't, right? This is just the potential as function of density at t equals 0. And we basically assume that the temperatures affect to first order are just from the thermal excitations of the states, right? That's why we just say your QMD itself acts like a hadron resonance gas. So the finite temperature excitation of pions and resonances, this is already included, but we do not put in an explicit temperature dependent of the equation of state, which should be done eventually, but it should be done through then probably a scalar density dependence. However, the reason why we said this might be still not too bad is, again, I try to motivate it with this plot. Where do I have it? Sorry. Here, where we showed lines of constant pressure. And if we are in this range over here, then we see that the pressure basically depends only on density and not explicitly much on temperature. That's why we said maybe for a first step, it's not so bad just to put in a density dependence and get like the temperature dependence only from the thermal heat bath of all the hadrons.
Okay.
There was a second question.
Yeah. Another question is, I heard from time to time that people saying that V1, it's sensitive to the phase transition at the minimum with a minimum point. So, do we have an intuitive explanation on that effect? Why V1 is low?
I try. We've been trying to understand how the V2 and the V1 works at low energy. So this is related also to the V2. So as you can see, the V2 is here also negative, and you know it's because of this. So what you have at low energies, you have the collision, right? You have the overlap, which is very similar to what happens at high energies, and then you have this almond-shaped overlap, right? And then with the pressure gradient being larger in the in-plane direction, your system starts to expand into the x direction, right? And this at high energies leads to the large V2. Now what happens at low energies, in this if it starts to expand in this direction, in the x direction, then there's still the spectators there because the overlap time is so long, right? This positive V2, which starts to develop, it gets blocked from the spectators. It's getting shadowed. And now this shadowing, first of all, leads then to the effect that the V2 becomes negative because only the ones, the protons which escape, they can escape into the transverse direction out of plane. But what this also means is that the V1 is a result of the shadowing, right? The V1 is a result of the strong V2, which is pushing out the spectators into the positive X direction, which is then giving a large positive V1. Now, what happens if you have a phase transition is that your initial V2 is just slower because you have a smaller pressure gradient. So basically, it means that the initial transverse push of the V2 is smaller, which then again pushes less on the spectators, which then generates a smaller V1. Right, so it's kind of this interaction between the early V2, which is positive, and depends on the equation of state, which then generates the V1. At least that's my understanding. I don't know if that helps you. Trying to write a paper about that.
Okay, that's interesting. Okay, good, thank you.
So, okay, next, Luo, please.
Yeah, hi, yeah. So very nice talk. Could you go to the HBT slide, next slide, I think so.
Yeah.
Yeah, actually I have two questions. One is that, so you know the R out square minus R side square denote about the emission duration of the particle, right? The lower observable. So it looks like why the dashed pink that is higher than this blue? It's okay. That means the first order has the longer.
Well, I would say these are almost identical within, this is almost the same as the blue, right? I mean, what you have is that when you have a very soft equation of state, you have just less push and your stuff gets emitted later, right? So you get longer emission time. That's the general idea.
Yeah, but you see the cascade one is also very high.
Right, because cascade is very soft. That's what people maybe don't realize. Cascade, you always, for me, cascade is like a huge phase transition. Because cascade, the potential here is zero, right? And if you look at what happens in reality when you have a normal, let's say, repulsive system, your potential is very positive. So you have extra pressure. While in the cascade, the pressure is very low. So the cascade looks almost like the phase transition in many observables. That's why it looks like this. So if you want to say, I want to compare my data to something which has a phase transition, just run the cascade. It's a good first order approximation.
Okay. Another question that you see that this at low energy, this R out square minus R side square, this show increased trend. So could you understand this? Yeah.
The minimum. Well, I think the minimum. Well, there's different ways of people are trying to understand this. There's this idea that you basically see the transition from baryon to meson-dominated matter, right? Because at low energies you have a lot of baryons and they have a very large cross section. So people say that the system just lives longer because of this large cross section. However, I think what you also have is that at this energy slowly, the kind of transition from the stopping regime to the transparency regime, and then you change the geometry of the system, right? At low energies, it's very spherically symmetric, but at high energies, you get this cylindrical shape where you have, right, the very high energies, you have boost invariance. And this transition also should then change how much matter is actually stopped at the central. I mean, this is for mid rapidity. So I think this is non-trivial. So it's both. So it's one hand, you kind of transitioning from baryon to meson-dominated, and that changes your cross-section and therefore your lifetime of the system, independent of the equation of state. And also you get this transition from the stopping regime to the transparency regime, which also changes somehow the geometry and therefore the lifetime of the system. At least that's my understanding.
does this trend depends on whether it is pi plus or pi minus?
No, it's the same.
It's the same.
At least for us, because I mean, but there you have to then also go into the question is how much does Coulomb affects
Coulomb
isospin potential, but which we don't. I mean, you can see it, right? I mean, the hardest data has small error bars and it's very small. And actually, I don't even understand how you can get negative values here, even how that's even physically possible, because that would mean you have instant emission or less than instant emission. So I don't think anybody understands it. Anyway, so we need better data here. And yes, also different charges. You may be able to study something. Maybe this has something to do with boson condensation. I have no idea. But this is something to understand. If we have good data in this region, then we can also start to understand it. Right now, it's, what was it going up, down here? I don't know. This is not useful, this HLS data.
Yes, I agree that actually fixed target program has collected data between 3 to 7.7 GB, and also we are measuring this pi plus pi minus separately for this HBT measurement. So hopefully,
I think this would be good.
Yeah. Okay. Thank you.
Thank you.
So okay, so Wu Laoshi, please.
Okay. Thank you for the talk. Can you go to the slide 4? Yeah, the accessibility.
Yep, this one.
Yes. I wonder why lattice peoples only show such as Chi2, Chi4. Why the people don't show the Chi3? Because we also interested in the scoreness.
Yeah. So the reason is very simple, because they can only calculate them at mu equals 0, right? Because of the sign problem, you cannot do lattice calculations at finite chemical potential. So the only which are non-zero are the even ones at mu equals 0. What you can do, you can kind of construct this the even ones using the uneven ones, but then they are just again a Taylor expansion of the uneven ones. So you would have to then. So it's not a direct measurement. So the only ones they can directly calculate on the lattice are the even cumulants, simply because they are limited to 0 density.
Oh, okay, thank you.
Hi, Ian. I have a small question. Can you go to slide 13? 13? Yeah, 13.
Okay, this one?
Yeah, this one. Yeah, I'm trying to understand your calculation. So when you perform the core collapse supernova, so how to justify this calculation? So I'm thinking that because we have the star merge data, but I'm not sure if for the supernova. So can you explore a little bit?
I can try. So you can look at this paper. So I didn't do this. So these simulations were done by Pia Jacobus, a former student, and Bernd Müller, who at Monash University. And what they have basically also a general relativistic hydrocode, which simulates these core collapse supernova. So basically, you do magneto-hydrodynamics, and you include general relativity, and you include some neutrino transport, and then you just, as for the mergers, you just put in your equation of state, and then you can simulate this stuff. That's as far as I understand it. If you want to know technical details, I don't know. Then you have to ask them, or you can look at this paper. Maybe then you
okay. Then we'll read the paper. So they also can perform the neutron star merge calculation, right?
In principle, they could, but I think technically it's different because it's different scales, and the initialization is different. I don't know why they are not doing it. I mean, it's a good question. In principle, it's the same kind of code, right? But maybe there are so many technical details which are different, so it's a big effort for them to. I don't know. I don't know why they are not doing it, but apparently there's groups who are doing merger simulations, and there's other groups who are doing supernova simulations, and they are not the same, right? So, but both are saying they're solving more or less the same type of equations, but I don't know why they're not so easy to interchange. I don't know.
Okay. Thank you.
Okay, so any questions? Okay, so Jen, I think it's almost the time. So thanks again for your
Thank you.
lecture.
Thank you very much.
Yes, I think if you have time, welcome to visit Fudan University in the near future. And
Well,
I think you will.
That depends. that depends.
That depends. Yes. Okay, so I think maybe today we're almost done. So see you next time. Okay.
Okay, thank you. See you soon.
Bye. Bye. Yeah.
Goodbye.
Bye.